Oh, I think I'm getting sick again. I even got a vaccine too. I'm so sick of getting the flu every single year.
True, and according to the Centers for Disease Control and Prevention, this year's vaccine only diminished your chances of getting the flu by 36%.
What if it was a way to completely prevent getting the flu virus?
Hi, I'm Dr. Claire.
Hi, I'm Dr. Ava.
Hi, I'm Dr. Leah.
Hi, I'm Dr. Emma.
And I'm Dr. Kathleen.
And together we are Team UC Berkeley.
There are 3 types of influenza viruses that affect humans, although only influenza A and B viruses cause the seasonal disease epidemics. When the flu virus enters the body, it moves into the respiratory tract, binding itself to the surface of cells. Once attached, it releases its genetic material, which is a single-stranded vRNA and some proteins, as a ribonucleoprotein, RNP. The RNP consists of many vRNA segments and proteins that are responsible for the replication and transcription of vRNA, translation of more viral proteins, and the degradation of host cell genetic material. The influenza virus mutates rapidly due to the absence of RNA profiling enzymes and vRNA segment reassortment.
The flu typically lasts 1 to 2 weeks, with severe symptoms in the first 2 to 3 days. Symptoms include weakness, fatigue, dry cough, and a reduced ability to exercise, and sometimes even fever, chills, and headaches.
In most cases, you'll need nothing more than bed rest and plenty of fluids to treat the flu, but there are times where your doctor may prescribe an antiviral medication, such as oseltamivir, also known as Tamiflu, or zanamivir, also known as Vilenza. If taken soon after you notice symptoms, these drugs may shorten your illness by a day and help prevent serious complications.
Antiviral medications are thus not suitable for everyone. In addition, side effects may include nausea and vomiting. And Tamiflu has also been associated with delirium and self-harm behaviors in teenagers. An additional concern is that some strains of influenza have become resistant to some antiviral drugs, including Tamiflu.
Today's expert agreed that the best way to prevent the flu is to get vaccinated each year. But in addition to the relatively low effectiveness rate of the vaccine, protection only begins about 2 weeks after vaccination. The vaccine is designed to protect people against 3 or 4 strains of the A and B flu viruses that researchers believe will be the most common in a certain year. So, every year, public health agencies make educated guesses and calculations on what strains and mutations will circulate in the upcoming season. For example, if you receive the vaccine protecting you from the influenza strand H1N1, but get infected by influenza strand H3N2, you are not protected.
Several research projects have already tried to genetically modify the virus's structure, but due to the rapid mutation, the results haven't lasted. We want to find a preventative solution that will stop our cells from becoming the host of the virus. Question is, how do we do that?
Our team is working on a solution based on the CRISPR-Cas9 editing of cells to prevent the ability of the influenza virus to hijack the host cell machinery by stopping the viral mRNA capping and subsequent viral protein translation in the host cells. CRISPR stands for Clustered Regularly Interspaced Palindromic Repeats. The name itself represents pieces of regular and reoccurring DNA that came to be in bacterial defense system to fight off viral invasions. The most common form of the gene editing tool is CRISPR-Cas9 and consists of 2 key molecules that introduce a mutation into the DNA. These are an enzyme called Cas9 and a guide ribonucleic acid. The Cas9 enzyme acts as a pair of molecular scissors that can cut the 2 strands of DNA at specific locations in the genome so that bits of DNA can then be added or removed. The second half of the gene editing tool is a piece of ribonucleic acid called guide RNA, also known as gRNA. This consists of a small piece of pre-designed RNA sequence that's about 20 bases long and located within a longer RNA scaffold. This scaffold part binds itself to the DNA, and then the pre-designed sequence guides the Cas9 to the right part of the genome. This makes sure that the Cas9 enzyme cuts at the right point in the genome. By using this technology, we would be able to prevent the virus from injecting its genetic material into our cells and therefore stopping it before getting infected by the virus.
If you are interested in knowing more about our solution,
Catch us at the bioengineering competition on the 7th of April 2019 at UC Berkeley.
thank you!